Hello everyone, I am Honargo. I am currently a PhD scholar at IIT Kanpur. Today we will discuss week 6 of the fundamentals of supersonic and hypersonic flow. I will generally discuss one problem and related concept to it. Many problems one by one and related concept to it. And most of the course, uh, whatever I am using is taken from Hypersonic and High Temperature Gas Dynamics by John D. Anderson. And some parts is also taken from Physical Gas Dynamics by Vincent T. If there is any doubt, you can ask in between also. This is the first problem. The most probable macrostate is associated with maximum number of microstates, thermodynamic non-equilibrium, thermodynamic equilibrium, maximum degeneracy. So what will be the answer for this problem? Are you able to hear my voice?
Yes, sir. Yes.
Okay. So what will be the answer for this problem? Yeah, it has multiple answers. So the most probable microstate, it is generally associated with thermodynamic equilibrium, and it can also be found using the maximum number of microstate. The microstate which have maximum number of microstate is also a most probable macrostate. Now we'll study slightly about these macrostate microstates. So internal energy of a molecule can have four types of energy, mainly four types of energy: translational, rotational, vibrational, and electronic. In translational energy, there are in each energy there are different levels, and because energy is always quantized. Generally, we think that energy is continuous, but it is not like that. Each mode of energy is quantized. In so there are different levels available for each energy mode. In translational energy, these energy modes are very near to each other. That's why it feels like continuous energy. In the case of rotational energy, as we increase the level, the energy difference between the two levels increases. And the initial level is called the ground level, ground state, or ground level. In the vibrational mode of energy, it is opposite of rotational energy. In this case, the energy difference between two conjugative levels decreases as we increase the level. Sorry, this is not, it is decreasing, this is all. And in the case of electronic energy, the difference between the first two energy level is very large. After that, it is also decreasing and very rapidly also. So if you see that if you wanted to excite a mode of energy, the least amount of energy will take in the translational energy. After that, it will take in the rotational energy, and there is big gap between rotational and vibrational energy. So it will take a huge amount of energy compared to rotational in the case of vibrational energy. Similarly, in the case of electronic energy also. And if you see, if there is one atom only, then it will have mainly only translational energy and electronic energy. This electronic energy is due to the electrons present in the atom. It will not have any rotational energy because uh, if if it rotates around its own axis, its value will not be very high. Similarly, in the case of vibrational energy also. But in case of molecule, let's say this is a molecule, and if it is rotating around the axis, then its uh, rotational energy will be high. because they are away from axis of rotation. Similarly, in the case of vibrational energy also, they will vibrate from their uh, center of mass from left to right. So it will also have a high amount of, it will also contain the vibrational energy. So total energy of a molecule can be given by, the energy is represented by epsilon dash. It will be the sum of translational energy, rotational energy, vibrational energy, and electronic energy. And if I have written here with epsilon dash 0 trans, epsilon dash 0 rot, epsilon dash 0 by, and epsilon dash 0 elect. These are the ground level energy in translational mode, rotational mode, vibrational mode, and electronic mode. And this ground state energy is taken at the absolute zero temperature. It is also called the 0 point energy. So the total 0 point energy of molecule will be the sum of translational, rotational, vibrational, and electronic. But at ground state, this rotational energy will be 0. So it will be only sum of these three energy. Is there any doubt till now? Okay.
No, sir.
Okay. So a energy level can also have different energy states. These different energy states will contain the same energy, but uh, uh, it will be different, because at the quantum level the energy is not only defined with the energy level but also with its direction of angular momentum also. Like this is one molecule, it is rotating like this, and this is the direction of its rotation angular momentum. This might be a different direction, this might be a different direction, because this angular momentum is also quantized. So all these will get the different state of the energy. These all have the same energy, but these are the different energy states. These are also distinguished with each other. So any given energy level epsilon I dash, there can be a number of different states that all have the same energy. This number of states is called the degeneracy or statistical weight of given level epsilon I dash, and is denoted by Gi dash. So this Gi dash is nothing but degeneracy, which is given by number of states having the same energy epsilon I. Now we will consider our system consisting of a fixed number of molecules n. Let Nj be the number of molecules in a given energy level epsilon j dash. So we have total n molecules, and these are distributed on different energy level. They are different energy level, and in each energy level this Nj molecule is there. In first energy level epsilon 1, epsilon 0 dash, and 0 molecule is there, epsilon 1 dash, and 1 molecule is there, and so on, epsilon j dash, and j molecule is there. So total energy will be total the number of molecule will be the sum of this n0, n1, and till nj. Not till nj, after nj also. So it will be the summation of nj. So if we look at our system of molecule at one instant of time, we will see a given set of nj. So what happens? There are different molecules are present in the system. So these molecules are having collision with each other. So if one instant, these are the number of molecules in this energy level. Due to collision, another instant, this number of molecules can change also. So at one instant, whatever is this population distribution Nj, it is called the instantaneous population distribution, or a macrostate. Because of this incessant molecular collision, some molecule will change from one energy level to another. Hence, when we look at our system at some other later instant, there might be a different set of Nj. Hence, a different population distribution on macrostate. So, with time, this macrostate can change. But what will happen that over time, there will be one particular macrostate which will occur more frequently than any other distribution. And this is called the most probable macrostate, and it occurs when system is in thermodynamic equilibrium. When system is in thermodynamic equilibrium, this macrostate, most probable macrostate, will occur, and it is generally denoted by Nj star. At an instant of time, the way molecules are distributed in different energy states define the microstate. So now this Nj is the number of molecule in epsilon j dash energy level, but this energy level also has Gj energy states. So this molecule will be distributed to this Gj energy states. So how they are distributed will also change the state of the system. That state, so this state is called the microstate. We'll see an example. Let's say total N is 5, and we have taken only two energy level, epsilon 0 dash and epsilon 1 dash, and in epsilon 0 dash number of molecule is 2, and in epsilon 1 dash number of molecule is 3, and this is 0 G0. We'll write it again. G0 equal to 4 and G1 equal to 5. So this is the degeneracy in epsilon 0 dash energy level, and this is the degeneracy in epsilon 1 dash energy level. So at one instant of time, the molecule are distributed like this. In G0 there are total 2 molecules, and they are distributed in 4. Let's say we are denoting this box as a energy state. One box denotes an energy state. So in G0 they are distributed like this, and in G1 they are distributed like this. And in some another instant, the distribution of molecule changed. So you see that here also, and this n equal to 2, n0 equal to 2, and n1 equal to 3. Here also n0 equal to 2 and n1 equal to 3. So you see that this macrostate is same. Macrostate is same, but the microstate is changed because the distribution of molecule inside the energy state is changed. There is one postulate which says that all microstates are equiprobable. It means that the probability of happening one microstate and with the other is always the same, and change in microstate occur due to the collisions, and there will be one macrostate which has the most number of microstates, and that will become the most probable macrostate. Let's say we have these different macrostate A, B, C, D, E, F, G, H, and they have different number of microstates. So these are the number of microstates. So you see that this D has the most number of microstates, and as we know that all the microstates are equiprobable, so the one macrostate which has the most number of microstates has the most probability of occurring. So it will be the most probable macrostate. Is there any doubt till now? So in this problem also it was asked that.
No, sir.
Okay. So in this problem also, it was asked that which most probable microstate will have most number of microstate, and it will also occur in the equilibrium only. It is associated with thermodynamic equilibrium. Now we will see the second problem. Total number of a given microstate for bosons is given by option A pi j nj plus gj factorial upon gj minus 1 factorial nj factorial. Here this pi is always used for multiplication, or you can say product. So it will give product of all the this variable which have this j. We are changing j and all the quantities are getting multiplied. And j is number of molecules in energy level FLMZ dash, and gj is degeneracy of FLMZ dash. And option B is pi j nj plus gj plus 1 factorial upon gj factorial nj factorial pi j nj plus gj minus 1 factorial upon gj plus 1 factorial nj plus 1 factorial pi j nj plus gj minus 1 factorial upon gj minus 1 factorial nj factorial. So what will the answer for this? It was taught in the class also.
Sir, option D, sir.
Option? Which option? I could not hear it. D.
Pi j nj plus gj minus 1 factorial divided by gj minus 1. Yes, sir. D.
This is the correct answer. So generally you can remember this also, and I will show the derivation of this, how we got this. So before we have seen how molecules are distributed in the microstate. So here in this example you might see that I have only distributed one molecule in one energy state, but there can also be distribution like where we are distributing multiple molecules in a single energy state. So the molecules which can be distributed in a single state also, energy state also, are called the bosons. So the bosons, for boson the number of molecules that can be in any one degenerate state is unlimited, except of course that it must be less than or equal to Nj. So if there is one degenerate state, this is the energy level FLM0 dash, let's say, and it has 5 degenerate states. It has 5 degenerate states. So in one degenerate state there can be unlimited number of molecules. But what is the condition? That this FLM0 dash energy state has N0 molecule. So this molecule should not be greater than this N0. It should always be greater than N0. Similarly, in case of FLMZ dash energy level. Now we will derive the expression for this microstate, number of microstate for bosons. We will consider only one energy level, FLMZ dash, and it has GJ degenerate state and MJ molecule. We will consider the GJ states as the GJ container diagram there. So here we have this GJ container 1, 2, 3 like this total GJ container, and this X denotes the molecule. So in each container we are giving the molecule, and this container are separated by one panel. These panels are separating the this container. So as there are GJ container, so how many panels will be there? Total GJ minus 1. To separate two boxes, we need only one panel. To separate three, we need two. For separating GJ boxes, we need GJ minus 1 panels. And there might be some boxes which have no molecule. It can be empty also. And it might be like that also, only one box contain all the molecules. So these molecules and these panels can be distributed we can find this permutation of this molecule and these panels. And if we move one molecule to another box, then we can get a different microstate. So the total number of permutation between X and this panel is given by Nj plus Gj minus 1 factorial. You can see it like this also. Let's say we have these three boxes. So we have two panel and total 3 molecules. So we can, if we move this panel here, so X, panel X, panel X, we can get a different microstate. Similarly, if we move this panel here, we might get a different microstate. So by changing the location of panel and molecule, we are getting a different microstate. So the total permutation we can do by changing the location is Nj plus Gj minus 1 factorial, because Gj minus 1s are panel and Nj are molecule. Gj container separated by Gj minus 1 partitions. Now this panel or partitions are indistinguishable, means all partitions are same. So either this part, because in this case we have considered the case where, let's say this is one microstate, we are interchanging these two panel partitions, then also it is counted here. So we have to consider that if these are indistinguishable, then these partition can be permuted by Gj minus 1 factorial times. So whatever the number we got here, we have to divide it by this number, then we will get the number of days in which these two can be permuted. But molecules are also indistinguishable. So Nj molecules can also be permuted by Nj factorial times. Hence the number of base Nj indistinguishable particles can be distributed in Gj states is Nj plus Gj minus 1 factorial, which we got before. But as these two are indistinguishable, so we are dividing it by it. Now we got this expression, but this is only for one energy level epsilon j dash. So if we have to consider all the energy level, then we have to multiply, we have to take the product for each energy level. So we will get total number of microstate in a macrostate is given by, it is denoted by W equal to pi j nj plus gj minus 1 factorial upon gj minus 1 factorial nj factorial, where this w is the function of this population distribution n0, n1, nj. It is also called the thermodynamic probability, and it is the measure of disorder. Using this w we can find the entropy also. So this was the answer of this problem. Pi nj plus gj minus 1 factorial upon gj minus 1 factorial nj factorial. Is there any doubt in this problem?
No, sir.
Okay. We'll see the next problem. Total number of microstates for a given microstate. I think there is some typo here in this problem. Here in previous problem also, the total number of microstates for a given is macrostate. Here also in this problem, the total number of microstates for a given macrostate for fermion is given by. Last problem was for bosons, this is for fermion. Often is pi gj plus 1 factorial upon gj minus nj plus 1 factorial nj factorial, pi j gj factorial upon gj minus nj factorial nj factorial, gj minus 1 factorial upon gj minus nj factorial nj plus 1 factorial, gj factorial upon gj plus nj factorial nj factorial. Similar to before, gj is the degeneracy for epsilon 3 dash energy state, and nj is the number of molecules in that energy state. So what will be the answer for this problem?
Sir, option B, sir.
Option B will be the answer, gj factorial upon gj minus nj factorial nj factorial. We will see the derivation of this also. So the difference between fermion and boson is that in boson, if let's say these are the energy states, bosons can be put inside one energy state, multiple bosons, but fermion cannot be put inside only one. Fermion will go inside the one energy state. So this is possible for bosons, but this is not possible for fermion. This is possible. So for fermion, only one molecule can be given in any given degenerate state at any instant. Like I told you before, only one molecule can go in a degenerate state. So the number of degenerate state should be greater than or equal to number of molecules in that energy level. Otherwise, if it is less than, let's say energy degenerate state is 3 and we have to fill 4 molecules, then we can put only 3 molecules, but we will not have place for 4th molecule. So this Gj should always be greater than or equal to Nj. Now we will consider one energy level, epsilon z dash, and this energy level has Gj degenerate states and Nj molecule. Similar to before, we will consider GJ states as GJ container. So these are the GJ container. Now we will take a molecule. This molecule, let's say we have one molecule X. This molecule can be put in how many ways? If we wanted to put this molecule inside this container, in how many ways it can be put? You can count also. It can be put inside this, inside this, inside this, inside this. So all GJ container are available to put this one molecule. So we can put this one molecule in GJ base. So first molecule can be put in GJ base. Now we will take next molecule. Now our one container is full. Any one container is full. So before GJ container were there, but now how many containers will be left? GJ minus 1. So second molecule can be put only in GJ minus 1 base. So we will repeat this process like this. Third molecule will be put in how many ways? GJ minus 2. Fourth, GJ minus 3. Similarly, njth molecule can be put inside in GJ minus nj plus 1 ways. So the total number of ways will be what? Multiplication of all these. GJ into GJ minus 1, GJ minus 2, and so on to GJ minus nj plus 1. We will multiply numerator and denominator by GJ minus nj factorial. So on the numerator, this term, if you see GJ minus 1, GJ minus nj plus 1, and GJ minus nj factorial, it will become total GJ factorial. So it will be equal to GJ factorial upon GJ minus nj factorial. Now one thing which we have not considered is that molecules are also indistinguishable. So they can be permuted in nj factorial ways. So the number of ways nj indistinguishable molecule can be distributed over GJ states will be given by GJ factorial upon GJ minus nj factorial into nj factorial. It is for only one energy level. So if we consider all energy level, then total number of microstates for a given macrostate is given by, this is the product W equal to pi j GJ factorial upon GJ minus nj factorial into nj factorial. And see, this is the answer. Is there any doubt in this problem?
No, sir.
Okay. We see the next problem. Boltzmann distribution in terms of partition function Q can be written as nj star equals to a nq gj e to the power minus epsilon j upon kt q upon n gj e to the power minus epsilon j upon kt n upon q gj e to the power minus epsilon j upon kt and q upon gj e to the power minus epsilon j upon kt. So here n is the total number of molecules, q is the partition function, gj is the degeneracy, and k is Boltzmann constant, and f FLNJ is that is the energy, zero level energy. So energy which is measured above 0 point. So what will be the answer for this one?
So C.
C will be the answer, NYQ GJ e to the power minus FLNG upon KT. So now we will see the Boltzmann distribution, but before the Boltzmann distribution, we will also see Bose-Einstein and Fermi-Dirac distribution. Before we have found the number of microstates for a given microstate, but we have not found the most probable. This NJ star is the most probable distribution. So for bosons and fermions, we have not found the most probable distribution. So we found find first the most probable distribution, then we'll see what is the Boltzmann distribution. So there are two statistics, Bose-Einstein statistics and Fermi-Dirac statistics. Bose-Einstein statistics is for bosons and Fermi-Dirac statistics is for fermions. First we will see the Bose-Einstein statistics. So for bosons, we have derived this relation, W equal to pi Nj plus Gj minus 1 factorial upon Gj minus 1 factorial Nj factorial. This is the number of microstates in a given macrostate. We'll take the logarithm of this, so we'll get the log W equal to, so if we take the log, then this pi will become sigma, because we are taking all these terms individually inside the log, and this numerator will become log Nj plus Gj minus 1 factorial. Denominator will be in terms of minus log Gj minus 1 factorial minus log Nj factorial. As number of molecules is generally very high, so Nj will be very greater than 1, and the translation energy levels are very closely spaced, so they can be grouped together and form the large number of degenerate states. So that's why Gj is also very greater than 1. So what will happen? This Nj plus Gj minus 1 will be approximately equal to Nj plus Gj, and Gj minus 1 will also be equal to Gj. And if there is also one formula, Stirling's formula, which gives the logarithm of the factorial. So log a factorial equal to a log a minus a, where a should be large, generally greater than 12 also it will get this result. So if we use our relation in log W, then here you see this one we are neglecting, so this is Nj plus Gj, and this will become only Gj. So log Nj plus Gj factorial will be Nj plus Gj log Nj plus Gj minus Nj plus Gj from Stirling formula, and the second term log Gj factorial, what will become minus Gj log Gj plus Gj, and the third term minus log Nj factorial will be minus Nj log Nj plus Nj. Here you can see this Nj will cancel out, and this gj will also cancel out. And now we are writing we are taking out multiplying this log nj plus gj inside this bracket. So this first term will be nj log nj plus gj, and we are writing this nj term with it. So minus nj log nj. Second term will be gj log nj plus gj, and we are writing this gj log vj with this term. We'll take nj common here, so we will get nj log 1 plus, and this nj will also divide, because log a minus log b will be log a upon b. So we are getting nj log 1 plus gj upon nj. Similarly for this term, we will get gj log nj upon gj plus 1. Is there any doubt till here?
No, sir.
Okay, if there is no doubt, we will proceed. So we call that W was function of population distribution. That means it is function of n0, n1 and nj. And to find the maximum value of W. Why do we have to find the maximum value? Because we have to find the most probable macro state. And what is the most probable macro state? Which has the maximum number of micro state. And W gives the maximum number of micro state. So we have to find the maximum number of this W. So if there is W is maximum, then log W will also be maximum. So we will take the derivative of this log W should be 0. And as W is function of this population density, so from the chain rule, we can write d log W equal to dou log W upon dou n0 dn0 plus dou log W upon dou n1 dn1 plus so on dou log W upon dou nj dnj plus and so on. It can be written in the summation also, which will be equal to sigma j dou log W upon dou nj dnj. We will find this term first, dou log W upon dou nj. So we have this term log W. We have to take its derivative with respect to nj. So if we take this its derivative with respect to nj, so you see this is the summation of term which has a different value of j. So all other term will be 0, because if all other term besides this n containing nj will be 0, so all other term will not have nj. So if we take the derivative this term only, so the first term will take with derivative with respect to nj, so it will become log 1 plus gj upon nj. Then its second part will be nj upon 1 plus gj upon nj, and the derivative of this will be minus gj upon nj square. For the second term, we have to take this derivative, so it will be gj upon nj plus gj plus 1, and derivative of this will be 1 upon gj. So this gj will cancel out, this 1 nj will cancel to 1 nj, and if you see, this term can be written as gj upon gj plus nj. This term also, if we multiply this nj inside, it will be minus gj upon nj plus gj. So this whole term will cancel out. So it will be equal to log 1 plus gj upon nj. We will put this term in the equation, this equation. So we get d log W equal to sigma j log 1 plus gj upon nj dnj. So we got this equation, but there are two constraints. That is the number of particles, total number of particles should be n, and one more is the total number of energy should be E, which is constant. So sigma Ng will be equal to n. If we take its derivative, it will become sigma dNg equal to 0. Second constant is there, sigma epsilon j dash Ng equal to E. So E is a total energy. So if we add the energy of each and every particle or molecule, we will get the total energy. So if we take its derivative, it will become sigma epsilon j dash dNg equal to 0. So we have these two constraints and this equation, and so we have to satisfy all these three. So in this type of problem, there is one method called Lagrange multiplier. So in this method, we multiply, if there are equality constraint, then we multiply this constant alpha and beta with the constraint, and we get this minus sigma j alpha dnj equal to 0 and minus sigma j beta epsilon j dash dnj equal to 0. And these equations are added with this equation, the maximization problem. So we will get sigma j, we are taking dnj common in all these equations. So we will get sigma j log 1 plus gj upon nj minus alpha minus beta epsilon j dash dnj equal to 0. So for it to be 0, this inside term should be 0. So this inside term should be 0. So log 1 plus gj upon nj minus alpha minus beta epsilon j equal to 0. We will take this here on the right hand side, and as this is log, if we remove the log, it will get exponential. So 1 plus gj upon nj equal to e to the power alpha into e to the power beta epsilon j dash. We will take one that side and we will find the nj. So nj, now this is the most probable distribution, so we are writing this nj as nj star. So nj star equal to gj upon e to the power alpha e to the power beta epsilon j dash minus 1. This we got the most probable distribution for the bosons. Is there any doubt here till here? If there is no doubt, we will see the Fermi-Dirac statistics. So this is for fermions, and for fermions we found the number of microstates for a macrostate as this: W equal to pi j gj factorial upon gj minus nj factorial nj factorial. We have to repeat the same process which we have done for Bose-Einstein statistics. We will take the logarithm of this, so we will get sigma j log gj factorial minus log gj minus nj factorial minus log nj factorial. Same as before, product will become summation for log, and these terms will be written like this: due to the formula log a upon b equal to log a minus log b. Now we will write this log gj factorial using the Stirling's formula. So from Stirling's formula, log a factorial equal to a log a minus a. So this log w will become sigma j. This log gj factorial will become gj log gj minus gj. Log nj factorial will become minus nj log nj plus nj. And this log gj minus nj will become minus gj minus nj log gj minus nj plus gj minus nj. Now this gj will cancel out and nj will also cancel out, and you will get sigma j gj log Gj minus Nj log Nj minus Gj minus Nj log Gj minus Nj. Similar to before, for most probable macrostate, d log W equal to 0, and this d log W can be written as sigma j dou log W upon dou Nj dNj from the chain rule of differentiation, as W is only dependent on population density, and this term should be equal to 0. Now we will find the value of dou log W upon dou Nj. So if we take the derivative, this term will be 0. This term will get minus log Nj minus 1. This third term we will get log Gj minus Nj and minus 1. Oh, sorry, plus 1. So this minus 1 and plus 1 will cancel, and these two terms can be written together, so it will become log Gj upon Nj minus 1. We substitute this terms in the d log W term equation. So we will get d log W equal to sigma j log Gj upon Nj minus 1 dNj equal to 0. So similar to before, we also have two constraint here also. The sigma Nj equal to n and sigma epsilon j dash Nj equal to e, which will give sigma dNj equal to 0 and sigma epsilon j dash dNj equal to 0. So using the logarithm multiplier, we will write this constant as minus sigma j epsilon alpha dnj equal to 0 and minus sigma j beta epsilon j dash dnj, and these two equations we add with d log W equation, so we will get this equation. So sigma j log Gj upon Nj minus 1 minus alpha minus beta epsilon j dash dnj equal to 0. We will take this, for this term should be equal to 0. So by keeping this term equal to 0, we will get log Gj upon Nj minus 1 equal to alpha plus beta epsilon j dash. If we remove the logarithm and simplify it, then we will get Nj star equal to Gj upon e to power f alpha e to power beta epsilon j dash plus e. Is there any doubt till now?
Perfect.
Okay. You should try driving all this equation yourself, so you will get the idea properly. So this we got for fermion. So check the equation for boson also. So the difference, you will find that only difference is here, this term plus or minus difference. Here for the boson, the denominator was e to power alpha e to power beta epsilon j dash minus 1, and for fermion it was this. So for low temperature, what will happen that most of the molecule will be on the ground state, near ground state and nearby the ground state, so they will be densely populated. So due to which this denominator term f e to power alpha e to power beta epsilon j dash and 1 might be comparable. But for the high temperature, the molecules are distributed over many energy levels, due to which there will be many energy states which might be empty. So this Gj will be very greater than Nj. So for this condition to be true, this denominator should be very high. to see it here. If we write it, this is Gj upon Nj will be equal to e to the power alpha e to the power beta epsilon j dash plus 1. So if this term is very greater than 1, then this term should also be greater than very greater than 1. And similarly for the bosons also. So we can ignore this one. If we ignore this one, then you can see that the most probable distribution which we will get is Nj star equal to Gj e to the power minus alpha e to the power minus beta epsilon j dash. And this will be for both bosons and fermions. And this is the limiting case, which is called the Boltzmann limit, and it is also called as the Boltzmann distribution. So I have not derived here, but this beta is equal to 1 by kt. This you can find using the entropy and energy relations. Now we know the value of beta but not alpha, so we'll take the one constraint n equal to sigma nj, and we put the value of nj. Nj is what? Gj e to the power minus alpha e to the power minus epsilon j dash upon kt. This e to the power minus alpha, and this will be equal to n. This e to the power minus alpha can come out because it is constant. So we'll get e to the power minus alpha equal to n upon sigma j Gj e to the power minus epsilon j dash upon kt. We'll substitute this in this most probable distribution. So we will get Nj star equal to n Gj e to the power minus epsilon j dash upon kt upon sigma j Gj e to the power minus epsilon j dash upon kt. So this is for Boltzmann distribution. In the problem also we have to find the Nj star most probable distribution for Boltzmann distribution only, but in the problem there was terms called partition function Q. We have not introduced it till now, and the energy was also taken from the zero level point energy. It is more measured about zero energy level or energy. So we have to convert it. So this epsilon j dash is equal to epsilon j plus epsilon 0, where this epsilon j is the energy above the zero level energy. This epsilon 0 is the zero level energy. Epsilon 0 is zero level energy, and epsilon j is energy above zero level energy. So we will substitute this epsilon j dash to epsilon j plus epsilon 0. So we can see this also e to the power e to the power minus epsilon j dash on kt. It can be written as e to the power minus epsilon j plus epsilon 0 kt. So these two terms can be separated. E to the power minus epsilon j upon kt, e to the power minus epsilon 0 upon kt. So that only was done here. Similarly in the denominator also. Now this epsilon 0 is constant, kt is also constant. So this term can be taken, this is out. This term can be taken out of the summation, and this two term will cancel out. So what we will get it, Ng star upon n equal to Gj e to the power minus epsilon j upon kt upon sigma j Gj e to the power minus epsilon j upon kt. This term in the denominator is called partition function and denoted by q. So we get the equation Ng star upon n equal to Gj e to the power minus epsilon j upon kt upon q. And the problem was also, it was asked. If Ng star equal to n upon q Gj e to the power minus epsilon j upon kt. In the problems also, pay attention to the symbol also, epsilon j and epsilon j dash. In the assignments problems also, because these two are different to each other. If in some option, let's say it was given epsilon j, then it might have been wrong. If in this option itself it was given epsilon dash, it might have been wrong. Because q does not depend on epsilon j, it depends on epsilon. Sorry, q does not depend on epsilon j dash, it depends on epsilon j only. So it is good to pay attention to symbols. Is there any doubt till now? If there is no doubt, we'll see the next problem. A specific internal energy is written as function of Q, as A RT dou log Q upon dou T at constant pressure, RT square dou log Q upon dou T constant volume, C RT square dou log Q upon dou T constant entropy, RT dou log Q upon dou P with constant temperature. What is the answer for this one? Okay, you will see the its solution. So the internal energy E is given by E equal to sigma j epsilon j and j star. We are taking star because we are finding it for equilibrium, and this internal energy is measured over 0 point. Now from the Boltzmann distribution, we have found that E equal to sigma, from the Boltzmann distribution in the just last problem, we have found that Ng star equal to n upon q Gj e to the power minus epsilon j upon kt. So E will become equal to sigma j epsilon j n upon q Gj e to the power minus epsilon j upon kt. If n by q is constant, so it can come out E equal to n by q sigma j Gj epsilon j e to the power minus epsilon j upon kt. This is the equation we will give it. Now we know that q equal to sigma j Gj e to the power minus epsilon j upon kt. Now we will take its derivative with respect to temperature, keeping volume constant. This u is the function of volume and temperature. We will show it later. But right now remember that this q is function of volume and temperature. So if we take its derivative with respect to temperature, keeping volume constant, we'll get sigma j. Gj is not dependent on temperature, so Gj, and this term will become minus epsilon j upon k minus 1 upon t square. And if you see this k, this minus minus will become plus, and kt square is constant, so it will come out, it will be 1 by kt square sigma j epsilon j gj e to the power minus epsilon j by kt. You see this was the same term as the energy, which was in the energy equation number 1. So we can find this term, and it can be written as kt square dou q by dou t at constant volume. We substitute this term in the equation 1, so we will get E equal to n by q kt square dou q by dou t at constant volume. This is the equation 2. Now this is the internal energy, but we have to find a specific internal energy. So what is the specific internal energy? Internal energy upon mass. So let's say m is the mass of a molecule, and total mass of the gas will be m into n, because n is the number of molecules. We will divide both sides with the m into n. So E by m into n, which is nothing but mass, will be specific internal energy, and this n will cancel out, and so we will get k by m t square upon q dou q by dou t at constant volume, and this k by m is nothing but r, which is specific gas constant. So we'll get equal to RT square upon Q dou Q by dou T at constant volume. This term 1 by Q dou Q by dou T at constant volume can also be written as dou log Q by dou T at constant volume. So we get equal to RT square dou log Q upon dou T at constant volume. So this P was the answer. Now next we will see the new problem. A specific internal energy in vibrational energy modes is given by A equal to 3 by 2 RT, B equal to HV upon KT upon HV upon KT by e to the power HV upon KT minus 1 RT cube, C 7 by 2 RT, D HV upon KT upon e to the power HV upon KT minus 1 RT. So we have to find specific internal energy in vibrational mode. Before, this specific internal energy was total internal energy. Total specific internal energy considering all energy modes. So first, there is one relation, I have not derived it, but Q equal to Q translational into Q rotational into Q vibrational into Q electronic. So this Q partition function is the product of all partition function obtained from different energy modes. If we take its log, then log Q will be equal to log Q trans plus log Q rotational plus log Q vibrational plus log Q electronic. And we have seen that electronic internal energy is given by equal to RT square dou log Q upon dou T at constant volume. So if you put this value of this log Q in this equation, then we'll get it will be equal to RT square dou log q translation upon dou t at constant volume plus RT square dou log q rotational upon dou t at constant volume plus RT square dou log q vibration upon dou t at constant volume plus RT square dou log q electronic upon dou t at constant volume. This is the internal energy due to translation motion mode. This is for rotational mode. This is for vibrational mode, and this is for electronic mode. So this will be electronic. So our specific internal energy will be sum of internal energy through transmission energy, rotational energy, due to vibration energy, due to electronic energy. Now we have to find electronic energy, internal energy due to vibrational mode. So it will be equal to RT square dou log q vibration upon dou t at constant volume. So we need to find q vibration. In vibrational energy mode, energy of a level is given by energy of a energy level is given by E vibrational equal to NhD. So Q will be sigma n Gn, where Gn is degeneration of vibrational mode. With energy level epsilon vibrational n. So Gn e to power minus epsilon n vibration upon kT. This epsilon n vibration will be substituted, and for vibration energy mode from quantum mechanics we get Gn equal to 1 for each mode. So it will come to sigma n equal to 0 to infinity e to power minus n h nu upon kT. So this summation will see on the side. We will see how this summation is got it. So this summation we can write this as for n equal to 0 e to power it will become 1. For n equal to 1 e to power minus h nu upon kT e to power minus 2h nu upon kT, and so on. You can see this is a geometrical series in which we are multiplying by e minus h nu e to power minus h nu upon kT. So our r is equal to, in the symmetrical series, our r is e to power minus h nu upon kT, and e is equal to 1. So for infinite geometrical series, its summation will be equal to 1 upon e minus r. So we got 1 upon a upon 1 minus r. So we got 1 upon 1 minus e to power minus h nu upon kT. Is Q vibration. And in the specific internal energy formula, we have to find the derivative of log Q vibration upon rho t. This at constant volume. For dou log Q vibration upon dou t at constant volume is equal to 1 upon Q vibration dou Q vibration upon dou t at constant volume. So 1 upon Q vibrational is equal to 1 upon e to power minus h nu upon q2 to the power minus 1. And if we take its derivative, Q vibrational, then first term will be minus 1 upon, we will take derivative by using chain rule, we get minus 1 upon 1 minus e to the power minus h nu upon kt square into minus e to the power minus h nu upon kt into minus h nu upon k into minus 1 upon t square. This minus minus will become plus, this minus minus will be plus. In the numerator we'll get e to the power minus h nu upon kt. This one power of this will remove one power here, and into h nu upon kt square upon 1 plus e to the power minus h nu upon kt. We are writing this h nu upon kt in 1 by t separately, and this e to the power minus h nu upon kt we will take it in the denominator, so we will get e to the power h nu upon kt minus 1. Hence, what will be the e? E will be rt square into dou log u by f upon dou t, which for we will substitute this here. So we will get E equal to h nu upon kt upon e to the power h nu upon kt minus 1 into rt. This term. So D will be our answer. Now we will see the next problem. So when translational and rotational modes are excited, the value of Cp for an atom will be. So option are A r by 2, B 3 r by 2, C 5 r by 2, D 7 r by 2. One thing to notice, this is for atom. So before that, we should know that what is Cp. Cp equal to Cv plus R, and what is Cv? Cv equal to dou E by dou T at constant volume. And what is E? E equal to RT square dou log Q upon dou T at constant volume. So if we found log Q, and in this one only two modes are excited. So log Q equal to log Q translational plus log Q rotational. And one thing to note is that this is for atom. So in atom only two mode, this rotational mode will not be there. So this Q rotational will be 1. So we will get this log Q equal to log Q translational for atom. So if we got this Q translational, we can get the value of Cp. So from before, this E translational was RT square dou log Q translational upon dou T at constant volume. And what is the Q translational? It is sigma j Gj translational e to the power minus epsilon j translational upon kt. So this is for energy level. Energy level J it is written, but if we write state by state, then it will be sigma I, sigma e to the power minus sigma epsilon I translation upon kt. This is for each state. So for a state, this is H. This is H and this is N. So don't be confused. This N1, N2, N3 are quantum number related to translational mode. So Fn trans equal to H square upon 8m, N1 square upon A1 square, plus N2 square upon A2 square, plus N3 square upon A3 square. A1, A3 and A3 are dimensions of the system. So if you put it there in the equation, we will get, as there are three number N1, N2, N3, we will get the summation for N1, N2 and N3. And the value of N1, N2, N3 can be only integer, or no, positive integer, N1 from 1, 2, 3 like this. And H is the Planck's constant. So the summation will be divided into 3. Sigma n1 equal to 1 to infinity, sigma n2 equal to 1 to infinity, sigma n3 equal to 1 to infinity. X into the power minus h square upon 8m into kt, this kt, n1 square upon a1 square, this is h, and this is n. n1 square upon a1 square plus n2 square upon a2 square plus n3 square upon a3 square. As n1 term will be independent of n2 and 3, and similarly n2 will be independent of n1 and 3, and n3 will be independent of n1 and n2. You can separate all these summations. For sigma n1 equal to 1 to infinity, e to the power minus h square upon 8m kt n1 square upon a1 square into sigma n2 equal to 1 to infinity, e to the power minus h square upon 8m kt n2 square upon a2 square, and sigma n3 equal to 1 to infinity, e to the power minus h square upon 8m kt n3 square upon a3 square. So due to close spacing in translational energy mode labels, the summation can be replaced by integral. So we will see only this one summation. So sigma n1 equal to 1 to infinity, e to the power minus h square upon 8m kt n1 square upon a1 square. We can write this as integration 0 to infinity, e to the power minus tau upon tau n1 square dn1. So this whole term we are writing as tau, not this minus sign included. This whole term we are writing as tau. So this integration value is given by 1 upon 2 under root pi upon tau. If we substitute this tau value, we will get this a1 upon h under root 2 pi mkt. This 2 pi mkt. So this is for one summation. There are total 3 summations. For first summation there was a1, for second there will be a2, for third there will be a3, and this term is common in all 3 terms, so we will get its power to the 3. So it will be this multiplication of a1, a2, a3, it will be the volume, because it was taken as a rectangular system, and this h will be h cube. For this all terms can be written together, so it will be q translation to 2 pi k mt upon h square to the power 3 by 2 into v. So we got the q translation. So we will get log q translational, which will be equal to log 2 pi mkt upon h square to the power 3 by 2 into v. it can be separated also. So it will be log t to the power 3 by 2 plus log 2 pi mk upon h cube to the power 3 by 2 into v. We have taken, we have applied the multiplication rule for the log. Addition rule of the log. And if we take its derivative, log u translational upon dou t at constant volume, this term will be 0 because it is independent of temperature. This 3 by 2 also I can keep it outside empty. So this term I will get as 3 by 2 into 1 by t. Log t derivative is 1 by t. So internal energy due to translational mode will be RT square dou log u trans upon dou t. At constant volume, it will equal to 3 by 2 RT. As there is no, this is atom, so there will be no rotational mode. So this will be the internal energy if only two modes are excited. Now you know that Cv is given by dou E by dou T at constant volume. So if we take its derivative, we get 3 by 2 R. And Cp is nothing but Cv plus R. So which will be equal to 5 by 2 R. So this 5 by 2 R will be the answer for atom. Let's say in the similar type of problem, we have to find the Cp for molecule. Let's say for diatomic molecule only. Then this we have to find this Q for this rotational mode also. We have to find Q rotational also. So for finding the Q rotational, this problem is over till here. Now we are considering for molecule, diatomic. So for diatomic molecule, we have to find Q rotational, and it is given by sigma Gj from J e to power minus epsilon J upon Kt. I have taken J here because this J is the quantum number related to rotational. J is the quantum number, and Gj is given by 2J plus 1. For each energy level, state generation is given by 2J plus 1. And this epsilon J is given by h square upon 8 pi square I j into j plus 1, where I is the moment of inertia of the molecule. So now we substitute this in the equation of Q rotational. So Q rotational equal to sigma j equal to 0 to infinity 2j plus 1 e to the power minus h square upon 8 pi square I kt j into j plus 1. In this case also the summation is replaced by an integral, and after replacing it you will get, for the integral we get Q rotational equal to 8 pi square I kt upon h square. Try solving it also, this integration here also now. We'll solve this integral here. Okay, so we'll write that there are many energy levels. We will also substitute this f integral 0 to infinity 2j plus 1 e to the power minus, for simplicity we'll substitute this capital A equal to minus h square upon 8 pi square I kt. So minus a j square plus j dj. Now we'll assume this j square plus j equal to y. So 2j plus 1 dj equal to dy. So we substitute this j square plus j equal to y in the integration. So Q rotational equal to integration. Our limit will become, for j equal to 0, y is also equal to 0, and j equal to infinity, y is also infinity. 2j plus 1 dj is substituted to dy. So we get e to the power minus a j square plus j is y dy. So its integration will be minus e to the power minus ay upon a from 0 to infinity. It will be minus 1 upon a e to the power infinity plus e to the power 0 upon a. This term will be 0. We will get this 1 upon a, and value of a was there should not be a minus here because we are not taking a minus with us. So value of A bars h square upon 8 pi square I k t. So this q rotational will be 8 pi square I k t upon h square. We'll take its log. So it can be written as 8 k square I k t upon n log equal to log distance. It can be separated as log t plus log is a k square I k upon h square. If we take its derivative with constant volume, then we will get 1 by t. So E rotational will be RT square dou log Q rotational upon dou T at constant volume. Which will be equal to RT. So now we have found this for rotational also. If there was excitation of vibrational energy mode also, so we have found the internal energy for vibrational mode also. We have not mentioned it here. This is vibrational. So we found for E vibrational also. So if we wanted to find CV, then it will be dou by dou T E translational plus E rotational plus E vibrational plus E electronic at constant volume. This for constant volume we found already 3 by 2R. This also, if we do the derivative, we will get R only. This you can do the derivation and find it. This E electronic energy, it can be found using spectroscopic data. So this will be the relation for CV. One thing is to note is that okay, I will do the first. I will find this, then I will mention that point. I will find this in the next problem. Next problem is identify whether the following two statements are true or false. Statement 1. Air is mainly composed of diatomic gases N2 and O2, and therefore at room temperature gamma equal to 1.4. Statement 2. Between the temperature 600 Kelvin and 2000 Kelvin at P equal to 1 atmosphere, the gamma varies as the vibrational energy mode is excited and it is function of temperature. So we have to find both statement are false. Statement 1 is true, statement 2 is false. Statement 1 is false, statement 2 is true. or both statements are true. So answer for this is both statements are true. So I will tell it by this curve. This curve is between CV and temperature. So initially when only translational mode is excited, the CV value will be 3/2. And when after as there is no much energy required for rotational mode also, this rotational mode is also excited at low temperature. So after some initial temperature of 3 or 4 Kelvin, you will get CV equal to 5/2. This for molecule only, because for the atom there will not be rotational mode. And after 600 Kelvin, the vibrational mode also get started getting excited. So this it will the value of CV vary with temperature. So the constant region for gamma is between 3 Kelvin to 600 Kelvin, where both translational and rotational mode are excited. So at room temperature also will be constant. You can see the CV equal to 5/2 here. CV equal to 5/2. Cp will be CV plus R, which will be equal to CV equal to 5/2 R. Okay, CV by R plot. So Cp will be equal to 7/2 R. So gamma will be Cp by Cv equal to 7/5 equal to 1.4. So when two modes are excited, gamma will be 1.4 and it will remain constant because it is not dependent on temperature. Now what happens when vibrational mode is excited? So here we have not found when vibrational mode is excited, it depends on temperature or not. If this dou E vibration upon dou T is dependent on temperature, then CV is also dependent on temperature. So dE vibration found the relation. This one. So we have to find its derivative with respect to temperature. So E vibrational was h nu upon kT upon e to the power h nu upon kT minus 1 into RT. We will find its derivative. It can also be written as h nu upon k r t square into 1 upon e to the power h nu upon kT minus 1. So dou E vibrational upon dou T at constant volume will be equal to minus 2 h nu r upon k dq 1 upon e to the power h nu upon kT minus 1 plus h nu r upon kT square into 1 upon e to the power h nu upon kT minus 1 whole square into e to the power h nu upon kT into h nu upon k minus 1 upon t square. So we will simplify it. First we will take common h nu r upon k tq. We get minus 2 upon e to the power h nu upon kt minus 1 minus h nu by kt e to the power h nu by kt upon e to the power h nu by kt minus 1 square. This term we should also have taken common. Okay. We'll take it common also. H nu r upon kt square kt cube into e to the power h nu upon kt minus 1. Here we take LCM e to the power h nu upon kt minus 1 minus 2 e to the power h nu upon kt plus 2 minus h nu upon kt e to the power h nu upon kt. Let me check for mistake. Oh, one mistake I made in the starting. If h nu upon kt into rt, it will be h nu upon r. This t square will not be here. So this term will also not be here. Sorry for the mistake. It will be this term. This term I will start again. Sorry for the mistake. Okay, so this term will be this minus will also be here. If h nu by r k is here, t square is not here. So its differentiation will be h nu by r into k. It will be square and it will be 1 minus. This is the differentiation. This minus minus will become plus, and here is h nu by k t whole square into r e to the power h nu upon kt upon e to the power h nu upon kt minus 1 whole square. So you can see that this depends on temperature. So the value of Cv, which we got from earlier, it will be equal to 3 by 2 r plus r plus h nu by qt whole square e to the power h nu by qt upon e to the power h nu by qt minus 1 whole square into r plus dou e electronic by dou t constant value. So this is the general relation for the Cv. If there is no rotational mode, you can ignore this. Generally for atom, this rotational vibration mode will not be there. Only for molecule it will be there. So now you can see this vibration term depends on the temperature. So it will be, so this gamma value will also, when vibration mode gets excited, then this gamma value will change with respect to temperature. Gamma will become the function of temperature. So you can see that this vibration mode is excited and it is function of temperature. So if Cv is function of temperature, then gamma is also function of temperature. Okay, so in this discussion and generally in the lectures also, generally the book Hypersonic and High Temperature Gas Dynamics is followed. So you can refer to it and try to solve the problems and derivation given in the book. You can also refer to the Physical Gas Dynamics by Vincent T. And if you have any doubt, you can post it in the discussion forum. And now we'll end our class here. Thank you.